So types or classes are first-class objects in Agda?
Yeah, sets and types, I mean, they're all just parameters. They're really the difference that you kind of run into. It's like when you define a function, this thing here has to be the name of a set. It can't be a constructor. You can't like throw a constructor up in a function type signature. But other than that, you have this really neat hierarchy of, like we ask, what is the type? What is the type of true? Well, true is of type Boolean. And Boolean, we say, what is the type of Boolean? Well, it's a set, or it's, set. And then you say, well, what's the type of set? It's set 1, right? Remember? So what's happening here is, to avoid Russell's paradox, there's this hierarchy, like every set is sort of parameterized by a meta-level natural number, right? So really set, when we say set, it's really set 0. So set 0 can't talk about other set zeros. It is of type set 1, and then like you say, well, what's the type of set 1? Well, it's set 2, and what's the type of set 99999? It's set 1 with that many zeros. So Agda allows, so maybe I wanted to pass in, maybe for this, it's not really a not prime anymore, but maybe I want to pass in a Boolean, and I want to return a set. So maybe I want to say, if x is true, then we're going to return a Boolean, else I want to return the set 1. So it's going to have a problem there because what I'm this x that it's trying to infer, it's inferring set, except sets can't talk about themselves, so it really needs this to be of set 1 in that case, because I'm passing a set as an argument. And so Agda allows you to generalize or abstract over the input set by passing in a level. And there's a built-in thing, oops, here goes my Unicode again. There's a built-in thing level. You have to import a module to get the name level. Open import agda.primitive. And so the nice thing about modules in Agda is that you can open them anywhere. Okay, so import Agda primitive means that now I can access anything in this module, but then they're like all strongly qualified. And if I open it, then what happens is all those names are thrown up to the top level, so I can just use level by itself. So that's the idea there. I didn't actually use that. So here, set, now we're really getting into dependent types, right? Set takes, I'm passing an argument here to set, which is the level that I said earlier. And now, hey, I like my thing here. It's still valid. I can still go back to Boolean to Boolean, true and, nope, false. Not is really false. That's true. Truer. So this is a common pattern you see everywhere. It's sort of like, it's kind of nice, except man, it gets really tiring to specify universe levels everywhere. Other systems do different things. I can't remember if New Perl, some version of New Perl, tried to assume that all the sets do have universe levels, and it tries to solve the constraints you're giving it. If you're passing in a set, then it assumes that it needs a set of one bigger than the other one and tries to solve that for you. Whereas in Agda, you just need to pass them all in. It doesn't look that, it looks pretty verbose right now. You can give it a different name, A or something. Or if you're really cool, you want to use the Unicode thing, you do \ELL, and you get this nice little L thingy. Yeah. But what the problem is, I'll show you the problem. It'll come quickly. All right. Do we need to take a break? I know this is kind of like a long lecture. Are we all good? Anyway, if you need to take a break, just go ahead. All right, so let us play with this a little bit. So now that we were kind of before we go super deep into, I'm going to go a little bit deeper into this direction and define equality for you. So let's introduce definition equality. All right, so now what we've been doing here is sort of let's see. I think I have some slides. That'll just give you an idea, right? So whoa, that's pretty small. So here we have if we have a function from set A to set B, we can give a name to the first one, A on the left, and right, that's a parameter on the second one. We did that kind of already here, right? Set actually can take a parameter, and that's the level. So now we ask the question, well, what is the type of set B? And notice set B, it takes an argument A. So set B has to be a function from something to something. All right. So, well, on the left side, it takes something of type, A, whatever A is, and we know what A is. It's of type set A. So on the left of the function is going to be set A. But what's on the right side? If you remember when we define sets, when we say some set name, we say is of type set. So the type of these data types is just set. So a dependent function is a function from something that ends up in set, or some hierarchy of set, if you will. And so that's what we have. Now, how do we create a set like that? Right? I gave you an example. There's kind of like the built-in one. Set has this built-in level concept, so that the Agda meta theory, like sets always have this parameter everywhere. But how do we create one for ourselves? And I'll show you. Notice set name ended in set. But watch, we can, we'll put set B as the name of it, right? And now here, well, it's of type set, but really, no, it's not of type set. It's going to be this function. So Agda, the way you define it, you put that function there in the top line. Remember when we define booleans up here, booleans just say of type set, and there's no functions happening up here at all. All right? So there, that's our type. So now for the constructors for it, there's a couple different options. Like how do we get values in this type signature? What does that even mean? It's kind of confusing. So remember, set B now has to take a parameter. So we can't, remember here, each of these constructors, we said false is of type Boolean, and true is of type Boolean, and come back to that. Right? So here, well, now set B, you just can't say set B by itself because it's expecting another argument. So you got to give it one. You have a couple options. If you know what set A is, sometimes you want to constrain it to a hard-coded value. Now, if you look at set B, the parameter, you're giving it the parameter constructor A, but each of these constructors can also take an argument, and in that case, you can use the A here as the argument to the set there. And that's kind of how we started, if you remember. We created a function that, hey, given something of type set A, now the next set actually depends on that value of what we gave it. So it looks like that. That's a pretty typical signature. And this is the other case where you give it a hard-coded value. So constructor 1 in that case, like if you say we have some value of type, now the value, right, normally we just said like values of type Boolean. Right? When I said my bool, we said my bool has type Boolean, and we said what's the specific value, it has type Boolean, but what's its value? Its value is true. In this case, now the type has extra parameters in it. Well, it's a set B with a constructor A as its value. In this case, since we've hard-coded it, constructor 1 doesn't take any parameters, so it's actually just the same, the constructor 1. In this more general case where the constructor has a parameter, if we give it a value, constructor 1 has to take a value. So constructor 1 now takes a value of whatever you pass it, in this case A. No, now these will have to match, right? Because I've constrained the type. So here I've constrained what set A has to be by these constructors. And so that's generally true, right? So, yeah.
CSTR is just shorthand for constraint.
Or a constructor. This is the constructor for A. So if A was a bool, this could be like true. something like that. This is a little abstract, but yeah, anyway, so in general, like when you have a lot of these names floating around, remember I said earlier, this name is only valid up through here. So each of these lines, all these names you give it are independent. And there's a way to make them, to improve that situation if you know they're all uniform. But first I'm going to show you what equality looks like. So equality is going to take, let's do equality over booleans only. So we want to say that two booleans are equal. So what I'll do is put two booleans up here. The intuition that we have here is that when we have some value of type, I'm going to say, now this is like a proof really. I'm going to say, I'm going to prove to you that true is equal to true. And that's kind of the intuition behind the type. And the proof is going to be what I put down here. Well, if you notice now, this is empty. There's no way I can actually prove that. But I'm going to give you a way to prove that. Some people call this REFL for reflexivity, whatever. I'll just call it equal for now. So equal takes in, if we pass in a Boolean, call it x, what we're going to get is that, well, we know that x is equal to x. It almost sounds so trivial that why would I even bother doing that? Except for, remember I said in Agda's type theory, you can substitute equals for equals anywhere. And we've defined not false to be equal to true. So anywhere we go, not false is going to be equal to true. So we can actually do that down here when we say not false. Now we have this statement that kind of makes some intuitive sense. This type is a proposition, right? You've heard of propositions as types. The type now we've created is like a proposition. We're saying that not false is really equal to true. But before I do that one, I will show you the super trivial case because that's kind of what it looks like we're doing. It's like, so now equal, if I type equal here, it takes one parameter. What I just did there, so instead of filling in the whole thing, if you type in something, you do Control-C, Control-R. R stands for refine. And refine is used in two cases. One, if you start typing something like a constructor and you don't know what the arguments are going to be yet, it will fill in that constructor name here, equal, and then it'll give you holes for all the rest of the arguments. If there were like 3 arguments, you'd have 3 holes there. The other option is, hey, maybe there's only one solution to this problem, and refine will give you the start of that solution. And it turns out there's only one way to create something of type equal, and that's equal. Now remember Control-C, Control-Comma when you're inside of a hole tells you what you're looking for. Well, you're looking for a Boolean. And so this type signature, now with this constructor, notice we're saying, give me something of type Boolean, and that has type equal of that specific value. So I'm constraining the type signature by this value here. So it's expecting something of type Boolean. So if I try to type in false, it's saying, hey, you're trying to create something of equal true, true, but you're passing in false. So that won't work. But if you pass in true here, then it's happy. Because essentially what it's doing when it's type checking, right when you said, is it lazy or not? It's taking this first argument and reducing that one, takes the second argument, reduces that one, and then when it looks at this term here, this value equal, it takes this argument and reduces that argument, and then says, hey, did they all reduce to the same value? Right? Agda is strongly normalizing, meaning every term is going to reduce down to a canonical term. And so once you reduce all these 3 canonical terms, are they all the same one? And that's effectively what we've done here. So we've proven true is equal to true, not very exciting. But, like I said, anywhere where we've created a definition, a definitional equality, right? Not false is defined to be true. Therefore, not false is also going to reduce down to true. Right? So now if we go back to this Control-C, Control-N, where we reduce or normalize an expression, like half of a REPL, and we type not false, and it reduces down to true, now we're kind of understanding why we want to do that, or kind of where it's starting to fit in. Because here, not false reduces to true, that reduces to true, that reduces to true. So we've made a statement where all these things reduce down to the same value. Like I said, just take that to the nth degree, right? If I put not false here, same thing. it type checks because they all reduce down to true. Well, I can put the not false down here too, because they all reduce down to the same value, or I can put true back over here. It's like all the same thing. It's kind of weird, but this is really, these two notions of the strongly normalizing, the fact that the constructors limit what happens up here in the type signatures, kind of gives you now a constraint. And now you can talk about constraints. You can build multiple constraints and so forth. There's a problem, though. And we'll see that more with natural numbers. Let me do a couple more. Right, I can make more complicated. If I do not of true, that ends up reducing down to the same thing. Plus, I'm getting tired of having to type true down here. So remember when I said things can be inferred? You're kind of giving two values up here, so it can kind of infer what the type of that is. And so now equal doesn't need a parameter anymore. But if Agda gets confused and it's not doing what you think, you can pass in true like that. Or you can pass in x equals true if you really need to.
Does that mean it has partial inference?
Yeah, partial inference, because in general the theory, you can't infer everything in the theory. But it tries to do like the common cases. And it's not really, they might add a little more inference here or there. And sometimes I'm actually surprised by what it can infer. Like I read a paper, kind of reply, hey, you can actually infer this like applicative thing. Like, wow, that was cool, I didn't know that. Many like reference this paper where they showed, hey, I had this special inference of Agda, and yeah. But sort of unsolvable problem in general, but in the particular cases we can make it helpful for us most of the time. What other things can we prove? Oh yeah, okay, let's start proving a little bit more fun things, right? We have all these functions, so what else can we prove? We prove like not true is equal to true, and those are pretty simple. We can also do stuff like and true is equal to true. And if you look at it, well, these are all definitionally true because I didn't have to do anything to show it, to prove it really. What I just looked at, true and true, well, it's like you take true here and true, well, that just gives me the second thing back, and that's going to reduce down to true. But what might not be obvious, let's prove that not is equal to not prime. Remember, we define not prime in terms of the if then else, and we define not here as a simple pattern match. So we can prove that that those two things return the same value. So given some Boolean, we're going to show that equals not of x is equal to not prime of x. So it's a proof of extensionality, right? Given the same inputs, these functions return the same outputs. Equal, whatever. So we have one parameter here, this Boolean. And now we look, can we, now it's like, okay, well, we just typed the equal thing, right? Well, not really, because what's happening here is it can't reduce, right? When we define not up here, that's really far up, we gave it specific values, but here we don't know what the value is yet, so we don't know what it's going to come out to just yet. And likewise for, well, the not prime, we we still don't really know. So what we have to do is we have to k-split on our argument enough that Agda can have definitional equalities out of it. So we k-split on false, and now we look at our goal. So if you do Control-C, Control-Comma, it kind of does this like, it partially normalizes it. And if you do Control-U first, and then Control-C, Control-Comma, that'll be not normalized at all. So it'll just give you it as it is. And if you do Control-U, like two Control-U's, and then Control-C, Control-Comma, then it'll try to normalize it as much as possible. And so I don't think the defaults are right there. I never use the simple case, except when I forget. But if you do the unnormalized case, Control-U, Control-C, Control-Comma, you'll see that what it's trying to do is it's trying to reduce not false on the left and the not prime of false on the right. But now we have a definitional equality of not false. It's true. And now if we look at not prime of false, we have a definitional equality of that too, because it's going to be able to reduce this guy also, right? It's kind of a nested thing. Well, it takes f, but then it calls this if, and if has a case for the false. It's going to return the second thing. So it turns out that these are going to turn out to be equal. And all that's saying is you have reduced the problem, the type thing here, enough that Agda can reduce both terms to the same value. In the second case, if we do same thing, right now it's in the true case, and if we do the fully normalized version, we find that, hey, equal both reduce down to false, and we're good to go. So then we get equal. So I don't know about you, but when I first saw proofs like this, I'm like, well, you put equal here, and it's like, proof doesn't make sense. But the kind of intuition is that we're creating these definitional equalities up here, and Agda can run these as many definitional equalities as it wants until it can't do anymore, and that's a canonical value. But the problem is, not all terms reduce down to something because you have this like other parameter here that's restricting what it can reduce down to. But if you break down that parameter and then you start looking at the individual cases, then you can kind of connect pieces together. And that connecting the pieces is what the proof is. And it turns out that it looks like a lot like functional programming. I mean, because essentially that's what we did. It's like we're returning a value here. This term has different types though, right? This term has, remember when we looked at the whole, the type it has is that equal not false is equal to not false. We have specific values in the types. Right, so another thing of like and, just one more proof on the Booleans, I think, and then we'll call it good. So with and, right, and false and anything is false, right? So let's use and, like false and, right? So if we give so given any Boolean, right? So, okay, here's a cool thing. The way you read this, remember, it's a total function. So you can kind of say for all Booleans there. Let me comment that out just for a moment, because you can actually type that. For all, and it's actually a thing in Agda. But it's not, the for all doesn't introduce totality. The language has totality in it. So right now, this is literally a synonym for just that. But what the for all does, the for all signature, or if you use the Unicode, you do \ALL and you get the cool looking for all. That's a syntactic sugar for a type inference. And the type inference, if you stick an underscore here, that's sort of the same as, so remember underscore has like different meanings in different places. In a type signature here, it means infer this type for me. And it turns out you can even stick a hole in there and sort of ask it. What's the type? If you go in a hole and hit Control-C, Control equals, that tells you what are the constraints of this hole, and you notice that this hole is constrained to be of type Boolean. So really there's only one solution for it, and so it can kind of infer that. And so for all, when you put the for all here, that's just a synonym for that. So if I type, right, let me do a comment here. So for that, the synonym for that is just for all x. So, so you can say for all x, but remember the for all didn't introduce the universality. The total functions in Agda introduced the totality. So you can say for all x, or you make it look cool and do all x like that. But really, it's not for any x of any type of whatever. It's really for all x for any Boolean x. And so sometimes you even see people doing like this, just because it kind of reads nice, right? For all x, for any Boolean, call it x, whatever. But really, this has no meaning once you've specified the type, because it's a synonym for that. But it can save you a lot of typing, right? You can say for all x, like that, and it sort of infer the type of x for me. And if you can even infer the value of x, like it's a set or something, and you're using that set later, then you can wrap it in curly braces, and it'll try to infer the type of x, and it'll also try to infer the value of x. It's kind of like a double inference there. But I kind of, I like total theory, total functions, and I kind of like keeping that in the signature. All right, so x. So what I want to say is that x and anything false and x is equal to false, right? Because that's kind of a property of and. So now this is kind of like a property. So given x, I do this all the time. You like type the x, and we can ask, can you solve it there? And it turns out that's solvable. And you're like, well, why is that solvable right away? Whereas the not you had to k-split. Well, because look, false on the left, on the left, and whatever is equal to false. So that's definitionally true. Now let's do the flip. Let's do the and false. And this is where type theorists cry in pain because they should be equally difficult to solve, right? So if we say x and false should be equal to false, right? Except we can't definitionally prove that. If we type equal here, it's not going to be happy. It's like, well, I can't really figure that out for you, sorry. So the reason is if you look at how we defined x again, we never look at the value of the right side in any of our definitions. So it can't start by looking at the right side and realize that, hey, if you put false on the right side, that it's always going to be equal to false. It's not definitionally true. But if you k-split, now what we have here, if you look, we're saying that false and false is equal to false. Okay, well now we have a definitional equality because up here false and something is false. So that's definitionally true. So we can put the equal in there. And in this case, we know that true and false is false. And if you kind of go back up, true and whatever equals the whatever. Well, the whatever in this case is false, which is equal to false. So we're good.
So why can't you just say and false underscore equal and false x equal? Does it have to be a constructor?
Like this? You want to say this and false equals false?
No, in the proof. In the proof, can't you say and dash false underscore equal? Well, you have to have two cases here.
Yes.
The reason why I have to have two cases is because, well, this is equivalent to this, right? I never use x up here. Right? The reason is because this term here has a single type. The type is literally this, right? False and some value, I don't know, an unknown Boolean value is always going to definitionally be false. In this case, when I have k-split, the type of this term is different. These are not the same equal. The term equal here has different types. And that's what k-splitting is doing, is it's articulating what are the two types there. In the top case, when we ask, what type is that, we find out the type has false in both positions. Because since we've k-split here, we've now said that this x is really false. So now the type on the right has a more specific type than this one did up here. And that's kind of the trick. So it's like if you get lost, if you have a property that solves, some other proof that solves what you want, you can use that proof, but k-splitting is often how you get started with proofs. All right. You can play around. There's quite a few other exercises if you want to fool around. Like, for example, if and only if, and XOR, you can show that you can show lots of stuff. Anyway, other examples like, if and only if is not of XOR and that kind of stuff, and NAND and not, and NAND is not and all that sort of thing. I'm going to jump to numbers because time is running a little short, quite a bit shorter. So, but hopefully I'm trying to communicate is that kind of the core theory of where are these equalities coming from and where are the types differing was a pretty subtle thing for me, and I never saw it in a lot of detail. But I kind of like this approach of playing around with things. Oh, the other thing is, equals is typically done as infix. So we could do something like equals with two equals. And in that case, that would make our proofs look a little nicer. So we can say stuff like equals there. But now we have to start like doing that everywhere.
Can you have type aliases that would help here, like defining the same?
Yeah. So we could do it. Let's do that, so we don't have to spend hours redoing this. So you don't even need a type alias. You can just literally say that equals that, and now say, oh, I don't like the equal down here. So if Agda can infer the type, you don't have to specify the signature. I mean, this is somewhat equivalent to has type. Remember underscores and type signatures just mean if this type has exactly one value, it's constrained to be a specific thing, and I don't care what it is. So if we go to the whole and we sort of look at, it's expecting something of type set1, remember? Because equal ultimately is a set, ultimately. So the type of this funky thing is really a higher level set. And it's actually constrained to be this specific type signature, a Boolean to Boolean to set.
Will the underscore infer value types?
Yep. To a point. With values, they have to be more tightly, like it won't, you can't put an underscore here, for example. But there are certain cases where you can do that. It's kind of hard for me to explain right at this point, but like if you have an empty record with no fields, like it can infer that type, so sometimes it's handy. If the term is very uniquely specified, then something. Okay, what do I want to do here? Oops. Right, Boolean to set. Right, so you can like fill it in if you want. Notice the type, right? Equal has type, blah, 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 blah. And we just said, hey, this double equal thing has that, and lo and behold, it has, this is like, you kind of see where this notation is coming from. It helps you read the types of what the capital equal means.
Could you put set 1 there instead? And that would still, in the, in the underscore equals underscore?
Oh, well, no, because this itself is of type set1, right? So it's
if that were passed as a parameter.
Yeah, like, so what is the type of this? And you paste in that, you get set1.
Got it.
Yeah. It's easy to get lost in these meta level stuff, and I easily get lost. All right, so let's play around a little bit with natural numbers. So what I've done with Booleans is the data is pretty simple. So if we have natural or something, a set where, in the simple case is, 0 is a natural number, and then sort of like adding 1 to some other natural number gives me the next natural number, right? So you can do funky stuff. Successor, it's called, it's like the next number, so forth. And then the first thing that pretty much everybody does is define addition. So you can define your addition, natural to natural to natural. So you can say x plus y equals blah, 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 blah. And if we case split on the left, we're going to run into the same problem we run with an and. Well, 0 plus anything is that thing, and the successor of like adding the two together. And this is sort of equivalent to, 1 plus x plus y is equal to 1 plus x plus y, right? That's kind of what's going on there. All right, so let's prove something about plus. I'm going to show you the same proof I just did with this thing here, and we'll experience the same sort of pain. But we will come out the better for it. So let's generalize our equal. Right now it's hard-coded to Booleans, but really I want to pass in a set, x or something. And I'm going to use that set here and that set here. Well now, okay, this can get kind of tiring. Because, remember, the scope of this x only goes there. So now what I would have to do is pass in, given some x of that some x, some set x, and given another implied argument that is the type of that x, then equal blah, 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 blah. Oh, right, but equals now takes a stronger parameter, right? But maybe I'll make that one. So you could like start making everything implied here, and then you kind of end up with the same thing. But man, this signature is getting really, really verbose when x is the same everywhere. So Agda gives you a little shorthand. If you move this thing over to the left, now the scoping is different. Before that, remember here, x is only scoped that far. But now when I move it left, the scope is the rest of the entire definition. So now I can use x anywhere throughout the whole thing. And that will save me some effort here, right? So x is the same there, x is the same there, there. And remember, if you want to super generalize it, let's super generalize it, right? We have, I don't know, A is a level. You don't use arrows on the left side. I don't know why they didn't put arrows there, but it really is an arrow. The signature is exactly the same as it was before. It's just a name scoping thing, right? What is the type of equal? It's still x. Notice the arrow here. 2x. The x is a set. 2x to x is a set. It's the same thing. It's just, I don't know. But when you start adding other stuff, they don't like arrows.
Can you define level? Or is that
No. Level is like, as the primitive thing says. In Aquamax, you can I do command and hover over something to go to the definition of it, which can open a module. It's control or middle button or something and other stuff. It's a postulate, and it's a built-in part of Agda. I mean, it's part of the meta theory, so you can't define it. You can give another name for it. So you can say, I don't know, renaming level to capital L or something, and then that has to be capital L. But that's about all you can do. Let's see. All right. So where am I? All right. Just infer that type. Now, so if we're passing in an extra level, then that needs to be of type that. Sorry, I got to use my level. So you have this is such a common pattern, you see this everywhere. Like if you open the standard library and look at some of the Agda code, given, if you have multiple parameters, you can do A, B, C, or they're all levels, except the problem is if you have an A, B level, you can't just say now if you want some other set Y is of set B, you have to make it separate. So if you have 3 levels, then you have to add, Z over here, and it just gets really verbose after a while. But anyway, back to this. All right, so now we have equal that takes any set. All of our existing code still works. We successfully abstracted over it. So let's do 0 plus x, right? We want to say that given any natural number that 0 plus x equals x. Does anybody think they know? Oh, right. Okay, so 0. Agda has a couple other sorts of built-in magic. If you use this little syntax when you define your number, basically it's saying the built-in thing for natural is my natural that I've defined here. That will allow me to use decimal notation wherever. So I could type in 5, and 5 is really the successor, 5 is really the successor of the successor of the successor, and you gotta have 5 sucks in there, a 0. Right? But 5 prime, you can also just type 5 once you use that syntax. All right? And then maybe you want to have a proof that 5 equals 5 prime. So you can say 5 equals 5 prime, just to verify that you're sensible, and it's true. It's the same thing. Reduces down the same value. It is literally just a syntactic sugar over that. Okay, so in this case, if we do a refine, Control-C, Control-R, there is only one solution. 0 plus x is definitionally equal to x, because that's how we defined it. 0 plus something is equal to that something. That's just the way it is. But unfortunately, we have to kind of pick sides. Now, x plus 0 is not going to be so easy. In fact, it's actually quite a bit harder than even this one up here. All right, so we say, if we go in the hole and say Control-C, Control-R, no introduction forms found, that means it really can't solve it for you. Yeah. So could you speak a little louder? I didn't quite hear. Yeah? This? Yeah, I define, remember up here I defined double equals to be the same as equals right here. It's my own operator. There's no built-in. There isn't really any built-in stuff. I mean, if you import other code or something. But I think by default, let me think. I mean, you get like the parens and these things, keywords like data and where. You know, there's not really a lot of default symbols that you get. I mean, the for all, right? The all. But if you don't separate them by spaces, I can like type, you know, I can stick the all in there. And that, you know. So most things have to be separated by spaces. All right, so let's case split on the x case, like we did with the ands. So now if we look at the type, Control U, Control C, Control comma, because the U means don't normalize it. 2 U's means fully normalize it. Nothing means somewhere in between, which I don't know why that exists. So 0 plus 0 equals 0, but if we fully normalize it, we see that, come on now, they normalize to the same value. So we're good. Control C, Control R, we have one unique solution, works out. Now this case, okay, we have a little bit of a problem. So if we look at the unnormalized, we see that the successor of x plus 0, remember function application binds more tightly initially, right? So this is parend like with a highlighted thing parend, and then adding the 0 as opposed to doing that. If we did I fully normalize that? Quit. Stop. Oh, I'm in the wrong spot.
Alright, can I just quickly see the definition for the recall?
Sure. Like this guy? The real deal?
Yes.
Yep, got to have a level, and now this set, x is a set of that specific level, and then you have to have the x and the x. Now this also thing you need is the final set has the same level as that set. Pardon?
Gloriously messed up.
Yeah. Pretty abstract. This is the built-in definition of equality, and actually we're going to kind of need that. Let me just grab that right now. So this is the fully generalized equality, and there's a built-in equality for this cool thing I'm going to show you right now. We call it that. We called it equal. I wonder if that's going to give me a problem that this one is different than that. I think it might. Okay, so if we fully normalize, we see that we have the successor of x plus 0 is equal to the successor of x. So that's not going to reduce. So remember, a general principle I specified before is that anywhere in Agda, if you have an equality, you can substitute equals for equals. Now, definitional equality, you can substitute that anywhere, no problem. In fact, you won't even notice it. Agda doesn't even notice the difference, because Agda, it's going to reduce, when it needs to know the canonical form, it's going to reduce it, and the definitional equalities are all going to go away. But you can but still, the Agda theory respects a propositional equality, just like we specified up here, like 5 equals 5. So now we can swap them in and out. The only problem is we need to carry that proof, and then the theory respects swapping equals for equals, but it doesn't allow you to do that everywhere. So what we have to do here is use a rewrite. So what we're going to do is we're going to rewrite x plus 0 of x. And that reduced. Now, okay, so before I jump on that, remember x plus 0 is this thing here, right? So what I did, so if I ask, what is the type of x, well, I can't do it right there. So before I had this, right, I had the successor of x plus 0 here equals the successor of x. Now I can get a proof if I recursively call this function, like kind of how we recursively called the plus for addition. If we recursively call this with this smaller x now, we will get a proof that x plus 0 is equal to x. And the idea with the rewrite is that if you have a proof of equality, you can replace in any expression everything of the left-hand side with the right-hand side. So when we fully reduce it, we see on the left-hand side is an x plus 0, and we want to replace that on the left with x. So when I say rewrite here, right, let's call this rewrite p. And I say where p equals that. And I guess it doesn't let me to do that in the midst of a rewrite. But that's kind of the idea. Here, let me show a little slide. I wrote up the slide last night, so it's a little rough. But the idea is somewhere, if we can show that we have an equality on hand where the left-hand side equals the right-hand side, wherever we see the left-hand side, we can replace it with the right-hand side. So effectively what we've done is now we've replaced the left-hand side, remember, which used to be successor of x plus 0. We've swapped that with its equals, which is x, and now the proof reduces. Now we can get the fact that they're equal. So that's one way to do it. Turns out rewrite is kind of like a super level construct. That you can also do this using a with expression. And you can also do this with congruence. And I want to show you congruence, because congruence, I think, is one of my favorite things here for equality.
Sorry, one question.
Yeah.
It's saying that built-in REFL is not found. There's no binding for built-in REFL.
You have Agda 251.
Your built-in statements are needed. You scroll up to your built-in, yeah.
So if you didn't put these two guys in there, yeah.
I didn't have the second one.
Okay, yeah, for whatever reason, this one, you need to give the type as a separate thing and the value, whereas with natural numbers.
Oh, you said that's commonly called REFL, the lowercase equal.
Yeah,
Okay. Thanks.
so if you call that REFL, I mean, that's usually called REFL for reflexivity.
Works kind of.
Yeah, so the rewrite requires you to use a built-in, something that's defined to be the built-in equality is all. If you did it with a with expression, I'll just show it to you. We only got 5 minutes, but the idea with a with expression is that you can sort of use the result of a kind of a function application or some expression down below. So it's kind of like adding, this ... is just a syntax for this, shorthand for that. So you can use, so it's kind of like adding an extra parameter. Now we got this our thing on our context because we've sort of called, if you will, or applied this function and got a result of x plus 0 equals x. The problem is it didn't, with is actually it's not like a part of the core language. It actually gets implemented in the core language of an auxiliary function. I can show you that briefly. But if you add an extra parameter, you just add these extra bars. So you have like R1 and R2. So now if we look at what's going on here, we have two natural numbers. We've kind of generalized over x plus 0. And with this proof now, we kind of have gotten that R1 is equal to x. And so now we get that if we have a proof that R1 is equal to x, and if we pattern match on that, okay, here's a cool thing. This dot syntax here means this value is constrained to be a specific expression. Because equality, remember the way we've defined equality, we're constraining these two things to be the same thing. So if we pattern match, before I pattern matched on the equals, so let's call this like x2 or something and call this the p. How about? So the p is a proof that x2 and x are equal. And if we pattern match on p, well, the only way they can be equal is if the second thing is really x. And so the dot is kind of, you can use underscore there too, means I don't care what the value is. But if you use a dot, you're saying it has to be constrained to be this expression. And it can actually be any expression, because you can even pass in functions when you define the type. So if x are constrained to be the same, then we know now that successor of x is equal to successor of x, and so we've solved the proof there. So that's another way to do it. And like I said before, this is actually implemented using auxiliary function. So before I had x2 here and x, or a p or something. So if we look at the type of this, well, our goal, it really just makes a function. So here we have a function. X plus 0 aux is of type. It ends in that, and it takes these three parameters. It takes x and x2 are natural numbers, and a proof p. Well, you don't really need the p here, but that we know that x2 is equal to x. So if we fill that guy out here, x plus 0 aux, and we have x, and so remember, when we give names of things, the scope is only that far. And we have this proof p. Notice we have something up here that looks pretty similar to down here. That's because this is what it's doing behind the scenes when you use the with expression. And when we match up there, it looks the same, because this is literally what it's doing. It's creating this auxiliary function. And now we can solve for equals. And instead of doing this, here I'll just comment that out so it's still kind of visible. Really, x plus 0 of successor of x equals, what did I do? Well, I gotta add a hole or something. If I call x plus 0 aux, it takes 3 parameters. So I'm going to pass in x, I'm going to pass in x plus 0, and remember, if I recursively call this function, it's going to, with x, it's going to return a proof that x plus 0 equals x. And so it solved it. And that's what doing with here is doing behind the scenes. It sort of allows you to add an extra parameter that can be constrained based on the results.
And just to clarify, you said that the dot in front of the second x is to say it's the same value as the first x?
In this case, because the expression here is x, but if there was some y somewhere else, the dot is saying whatever is, so I can give it a parentheses, whatever the expression is in here is constrained by something else. It's kind of a constraint. I can't remember what they call it. But since if you have two natural numbers and you have a proof that they're equal, the only way they can be equal is if they're reduced down to the same value. And so that way, even in our pattern matching, we can see the result of that. And that's kind of how it looks syntactically. If I just said x here, it won't be happy because it's like, well, you're trying to repeat the same variable name. Whereas what you're saying here is that when you use dot, you're saying it's constrained, and now this isn't a name, it's actually an expression coming from this one here. All right. Yes?
Could you use that dot to define your equal constructor? It seems like,
No, well, I didn't need to. When I defined the equal constructor, all I did is I just used the same thing. And so that's kind of where it's coming from. It's like, hey, this second one has to be the same as this one.
I guess if you say equal to two characters, and then the second constraint you think and then equal.
Yeah, no, unfortunately, the dot is only used in the pattern matching. But yeah, theoretically, right, you could say x and y, then... Well, the problem is, how would you say y over here, right? You kind of have, you have to say something like, y is really x, but, I don't... The way you just do that is you just give me one parameter and then they're the same. And then the two, notice the two parameters come in the type signature there. So I can express something like 5 equals 6 by saying 5 equals 6. Except the problem is, well, how are you going to... You can express that as a type, but you can never... The final thing, I'm 1 minute over, but I want to share with you proof of negation real quickly. And that is, so if you can't ever prove a statement like this, but to prove it's false, what you do is you define a function from that to the empty set. And that's equivalent to saying 5 is not equal to 6. So the idea with negation is, right? Right, yeah, so on the left, if the right side is empty, how are you going to map everything of a non-empty set to empty? Well, you can't. So essentially, you have to convince Agda to create a function to an empty set. You have to convince Agda that the left side is empty. And in this case, it's going to figure it out right away. It's a function, so really this is like some p here of equality, or e. And if you pattern match on it, Agda, like, this is the syntax for, hey, this is impossible. And unfortunately, I didn't get enough time, but sometimes you can't convince Agda that it's impossible, so you have to do some extra case splitting or something until you can get it to a place where Agda can definitionally... What's essentially happening is you're reducing some expression, and you're saying, well, x in some case should really equal the successor of something, and in another case, you find that it really should equal 0. So now you have like the constructors, if Agda finds a constraint where the same thing should be one constructor and the same thing should be a separate constructor, that's a contradiction, and that will, that's what's happening here, is Agda's kind of reducing it and finding that's the case and allowing it to map to the empty set there.
So constructors have to have disjoint ranges?
They don't have to, but it will be considered a contradiction if a variable will be constrained to two separate things, right? So I could just add an extra equal here and just call it equal prime or something, right? That won't work, and that won't work, and the rest of the file will be unhappy. But I can create a type like that. But if for some reason Agda, in reducing something like this, gets one equal on the left and one equal prime on the right, it's going to consider that a contradiction, because you're constraining it and it kind of end up in different paths. I don't know if that would probably indicate, this is kind of indicating a weird thing with your model. If you don't want that to be a contradiction, then that could be a problem. But with something like a less than or equal to relationship, it's okay for it to be flipped, because sometimes it is true that x is less than or equal to y and y is less than or equal to x. In fact, then you can prove that the x and y are equal in that case as a natural number. All right, that's over time, so thank you very much.